correlation. I mentioned this yesterday, but very important to keep mentioning. Correlation in statistics is an actual value. So even though I know that at some point, I'm sure you will be wanting to say the correlation between this variable and this variable is, you cannot say that if you're going to talk about direction, form, and strength, right? That would you talk about just a relationship or talk about an association. If you're going to say the correlation between two variables, you need to then follow that up with a number, okay? So correlation is an actual numerical value. That's very important, okay? So some things to think about before we start getting into it. Here you have two scatter plots, and you have height in inches and weight in pounds in the one on the left. Then you have height in centimeters and weight in kilograms in the one on the right. So it's important to note that when you start changing units, that the direction, form, and strength really doesn't change. Okay, does that make sense? You've changed the units, but you haven't really changed the relationship between the variables. Okay, so changing units isn't going to change what we've been talking about with the association. All right. So they took that height and weight situation, and in order to find correlation, the first thing that they do is you go through and you standardize every single point. You are at no point going to do this by hand, so don't worry about it. But you do need to understand where it comes from. So you go through and standardize every single data point. All right. You guys have seen the z-score formula before. So all they do is for each point, they standardize x and they standardize y. That's all this is both z-scores. All right. By standardizing everything, we have now changed the scale a bit, but now we have something that has no units. So it really doesn't matter if we're in centimeters or inches or anything, right? Because z-scores don't have any units. And it makes the mean of both of the variables 0. So now the scatter plot is around the origin. All right. So then we have, this is the same information with height and weight, okay, but now it's around the origin. So I did not put all the rest of this up here because it gets into detail and we're not going to calculate it by hand, but in order to calculate the correlation, they start looking to see what points would show a positive relationship and what points would show a negative relationship and what points would show zero relationship at all. All right. So to do that, they start multiplying the z-scores at each point. Okay. If the point has a positive x and a positive y, when you multiply them, then that would be a positive, right, product. And so that would indicate a positive direction. If you had points that had a x or y that was negative and the other one was positive, when you multiply those together, that would indicate a negative direction, right? And then if you had any points that were on an axis, right, that means one of the z-scores was 0. When you multiplied them, you get a 0, right? And they would have no weight on the direction, okay? So to find the correlation, they're going to multiply the x and y for all the points to figure out what direction it's going to be in. And they're going to add them all up, okay? And then we're going to divide by n minus 1, just like they did with the standard deviation, and I still haven't explained why they do that yet, and that's okay. Now, you don't need to know that formula, because you're never going to do this by hand. You do not have time to take 30 points from a scatter plot and change all of them into z-scores, and then multiply all of the points, and then add them all together. You just don't have time to do that. No one realistically is going to ask you to do that, okay? But I want you to know where it comes from, because that kind of leads into some things. You do need to know that the correlation coefficient, as it's called, is represented by the letter R, okay? It will always be R forever and always, and if you see R equals anything, or you see R in a formula in statistics, it's talking about the correlation. So that part is important, okay? Now, the correlation coefficient is giving you a measure of strength all right, it's going to tell you how strong the relationship is, okay? So it goes on here, and it says for the students' heights and weights, the correlation is 0.644, all right? And we're going to talk about what that means. But that is a measure of strength. You need some context for that. But I can tell you this right now, that the sign of the correlation should match the direction. So since this correlation is 0.644, then I know at least that the correlation is positive. It's showing that it's a positive direction. So if it's negative 0.644, I would be showing a negative direction. right? So we knew that already. If we looked at the scatter plots, the first thing we knew was positive, right? So it should match. So if it doesn't match, then something weird is happening. You need to go back and look at some things. Okay. So far, so you need to know is how we got to the correlation, and that correlation is R. Any questions about that? All right. Then if you're going to use the correlation, you need to have 3 things you check for, right? 3 things. First, you need to make sure it's a quantitative variable or variables. You have 2 quantitative variables. Do not get tricked. On the homework tonight, a lot of the homework is going to say, criticize this statement, or can these statements be justified? And it'll be your responsibility to think about things we've talked about today to decide that. For example, if they say, criticize the statement, there is a correlation, or the correlation between favorite color and height is 0.72. Well, there's no way there's a correlation between favorite color and height, since favorite color is not a quantitative variable. Okay, so you have to guarantee that you have quantitative variables if you're going to use the correlation coefficient. Correlation also only works for linear associations. Right, we're talking about, part of this is talking about direction being positive or negative. If it's not linear, it's going to be hard to be positive or negative. If it's curved, that's going to be tricky because correlation is really going back to, it's kind of giving you a slope of a line, right? So you can only do this for linear forms. If it's not linear, don't use the correlation. And then outliers, we talked about this yesterday. If there is an outlier that if you removed it would affect your decision about direction, form, or strength, then you need to do the correlation without that outlier. Now, if it's an outlier that does not affect anything, then you don't have to worry about it as much. But if it's an outlier that affects the direction, form, or strength when you remove it, then you would want to report the correlation both ways. Well, like if you have some points that are pretty close together, and then you have one that's like out here, doesn't really change anything, right? But if you have a bunch of points like this, and then a point out here, and I took that point away, then there wouldn't be a direction or a form or really any strength to it, right? So it just kind of depends on what kind of outliers we're looking at. But definitely ones that are going to affect any of those measures are going to, or any of those pieces of the association will be important to get rid of. All right. You have to check those 3 things. 2 quantitative variables, linear, and outliers, if you can. If you can't, then those 3 things should be floating around your head. So on the homework tonight, it says, can you justify this statement? You should be thinking about those things. Well, I could justify that if I knew it was linear. Or I could justify that if I knew there were no outliers. But if you don't have a picture, you don't know, right? So just keep those things in the back of your mind. All right. Now here are some things you need to know about correlation specifically. There's a lot of them, but they're all very important. We already said the first one. The sign of the correlation gives the direction. If it's positive, it's positive. If it's negative, it's negative. No big deal. The next one's very important. The correlation is always between -1 and +1. Okay? The closer the correlation is to -1 or +1, the stronger it is. Okay? Think about a slope of a line that has a slope of 1. Right? If your correlation is 1, then it's essentially making a straight line, and it's not deviating from that straight line. If your correlation is 0.9, that's very strong, or that relationship is very strong. It's not a straight line, but it's very tightly compacted. All right? If your correlation is 0.7, still fairly strong, not as compact. Okay? Same thing for -1. So the closer it gets to 1 or -1, the stronger it is. So if you have a correlation of -1, that means that it is a straight line, but just going in the negative direction. If you have a correlation that's -0.9, very strong, just going in the negative direction. So it's stronger towards 1 and -1, which means it's weaker towards 0. So if you have a correlation of 0.02, not strong. Right? That is a very weak association. Okay? Correlation treats X and Y symmetrically. That means, like the first example had height as the x-axis and weight as the y-axis. If you flip them and make weight the x-axis and height the y-axis, by switching them, you don't change the correlation. Right? Again, think about how they calculate it. They standardize all the scores, and then they multiplied all the x and y's to get, like they're all multiplied together. So it doesn't matter if you change the variables from one axis to the other. Okay? Correlation has no units because it's based on z-scores. So it doesn't matter if you're in centimeters or kilograms or whatever. Correlation is just a number without any units. Just like standard deviation when we did z-scores. You had standard deviations above or below the mean. You didn't have actual units. Correlation is not affected by changes in the center or scale. We already looked at the scatter plots in the beginning, and we understand, hopefully, that by changing the scale, by changing the units in the original scatter plot, that doesn't matter, because it doesn't change the direction, form, or strength. It also doesn't matter if you change anything in the center. So if you're going to add 15 points or 15 inches to everyone's height, you're just shifting that data, right? You haven't changed the direction, form, or strength. So the correlation will still be the same. We said this, but correlation measures the strength of a linear association. Now, that does not mean that association cannot be strong if it's not linear, all right? So last night on some of the ones you were looking at, some of the pictures you were trying to match with what kind of associations they had, you could have had a scatter plot that made a very pretty parabola. Look at that, isn't that great? Now, all the points are tight and compact, and there's a definite form, right? So we would say that's a very strong relationship between whatever the variables were. Does that make sense? But because it's not linear, if you tried to calculate the correlation, it's going to tell you the correlation is like 0.2 or something. All right? Well, that correlation would indicate that it has a very weak association. Well, that's because it's not linear. All right? So correlation has to be linear. If it's not linear, then you can't really guarantee that what you're doing is correct. And the last one, correlation is sensitive to outliers. A single outlying value can make a small correlation large or make a large one small. So again, we've talked about this example several times. But if you have a cloud of points and then this one outlier, well, that one outlier makes it linear. And so it's going to make the correlation stronger because it's going to make it into more of a line. But if you removed that, then you just have this cloud of points and your association is weak. So your correlation would be low because that's not really linear anyway. Okay? So those are some things to think about today. Any questions so far about correlation? All right. Then we're going to do a just checking question, and then the last thing we're going to do is show you how to find the correlation coefficient in your calculator. Because again, we're not ever going to do this by hand. No one's got time for that. All right, so here is the question. Your stats teacher tells you that the correlation between the scores, points out of 50, on exam 1 and exam 2 was 0.75. All right, so exam 1 is one variable x or y, and exam 2 is the other variable x or y. Doesn't really matter which way they go. Before answering any questions about the correlation, what would you like to see and why? What would you like to see before we talked about correlation? I would like to see a scatter plot. But why would I like to see the scatter plot? What are the three things? I need to make sure it's linear, because I don't know. I need to make sure there's no outliers, because I don't know. And the one thing I do know is we have two quantitative variables, right? So I do know that. But I would love to see a scatter plot, because I need to ensure this is linear and ensure that there are no outliers. Just because they give you the correlation of 0.75 does not mean it's linear. Right? If they give you a correlation, you can just assume it's linear because they gave you one. Questions about that? All right, on number 2. If she adds 10 points to each exam 1 score, how will this change the correlation? I don't know what that means. If you add 10 points to every exam 1 score, it just shifts the exam 1 scores up, right? So does it change the direction, form, or strength? No. So correlation stays the same. Okay? If she standardizes scores on each exam, how will this affect the correlation? It won't. That's how you find correlation. You standardize all the scores, right? So it stays the same. Doesn't matter. Okay? On the next one, in general, if someone did poorly on exam 1, are they likely to have done poorly or well on exam 2? Well, so if we have exam 1 and exam 2, the correlation is 0.75, so it indicates that it's positive, right? If you did poorly on exam 1, did you do well or poorly on exam 2? Poorly. And on 5, it says if someone did poorly on exam 1, can you be sure that they did poorly on exam 2? No, there could be a point up here. You don't know, right? You don't have a picture, so you don't know. So you can't guarantee that. You could guarantee it if the correlation was 1. But if it was exactly 1, it makes a perfectly perfect straight line. But it's not 1. It's 0.75. So that gives you room for some different things going on, right? Questions about that? All right. So the last thing I want to show you is how to find correlation coefficients in your calculator. This is the data I used yesterday in class because it's already in the calculator on my computer and I don't have to retype anything. Okay? So if you want to retype it and do this with me, you can. There's only 7 points, not a big deal. If you don't recall how to do any of these things after I teach you today, it's all on that note sheet I gave you yesterday about how to make scatter plots. It's at the bottom. It's a 2-parter yesterday. Wait. Okay. Clay, I'm going to have to look up the directions for how to do this in a second. I don't know. Yeah, you should be able to find it. Because you've done stuff before in the same menu, so you'll be able to find it. Yeah, but I never know. We're always using different menus, places, but this one you've used before, so you should be fine. Stupid fancy calculator. Okay, first thing you need to do. Now, I actually learned something this morning, but I'm going to show you the old way first anyway, because it's just a good life tip for your calculator. But then I'll show you the short way too, because I learned something in first period. So I'm very excited about it. First thing is you have to make sure that the statistic diagnostics are on in your calculator, because if you don't, then when we do what we're about ready to do in a second, you won't get all the information and you won't have R, which is the whole point of doing this. We want to find R. So the way that I knew how to do it before this morning, I never remember where that is, okay, because I just can't find things sometimes. So I always go to second 0, and that's the catalog button. If you know that there is a function in your calculator and you do not know where to find it, for example, we're going to use normal CDF in this class like 50,000 times after Christmas, all right? And let's say you're having a moment and you do not remember where normal CDF is. Instead of clicking a bunch of random buttons and trying to find it for 5 minutes, you can always go to catalog and then go down to N and find normal CDF. Correlation. So we're actually trying to find right now, I don't remember where diagnostic is, so we need to change it to D. And if you scroll down, there's a place for diagnostic on and off. We want to hit diagnostic on. What do you mean, what are you looking for? We were just talking about how you can use the catalog feature. Just go to D. So you can actually just click the D button. Yeah, once you hit enter, it should just be done. It just turns stuff on the back of your calculator. Like, it doesn't actually do anything for you on the actual screen. Now, this morning, learn something new every day. I learned that this is actually a mode in your calculator. Who knew? So you go to the mode button, and you scroll down. It has stat diagnostics. You can turn them on and off there. I think that the reason I didn't know that is because the old calculators didn't have that, right? So the 83s don't have that. So you need to make sure you just go to catalog. I'm pretty sure that came with the update. That's why I didn't never know where it was. Once you turn it on, it should stay on. I think just that's what the standard like operating system. It just turns it off whenever you update it or whatever. It just has it off. If your battery dies, you'll have to turn it back on again because it reverts back to whatever the settings were. Okay. Now, you will know if they're off. All right. So if you try to do what we're going to do, you'll know that they're off. You'll go back, turn them back on. It's not the end of the world. Okay. So now that we have everything on, we're going to go and try to find R, correlation coefficient. So you go to stat again. This time scroll over to calculate where we've been doing like one variable stats and all that. And you're going to scroll down to number 8. I know that there are 2 linear regression functions. There's one on 4 and one on 8. We're going to use the one on 8 all the time because of stuff we're going to do in chapter 8. All right, so we're going to use number 8. Okay, we'll give you the same answer number 4, but we're going to be using number 8 in this class, so just get used to it. So click number 8, put in your X list and Y list, so list 1, list 2, unless you did them on weird lists, put in your list 3, list 5, whatever. And for now, you can ignore everything else because it doesn't really matter. It will matter in chapter 8. And hit calculate, and you should get a screen like this. Now, if your diagnostics were off, I'm telling you, you would know because these 2 lines would be missing. It would just stop. All right. So if your diagnostics were off, you wouldn't see what we needed to see anyway, and you have to go back and fix it. All right. So you should have R and R squared. We'll talk about R squared in chapter 8 as well. Right now, all I'm interested in is R. Everything else on that screen is actually important. We just haven't gotten there yet. Okay. So it says that for the fat and calorie scatter plot, all right, fat and calorie scatter plot, that the correlation coefficient is 0.96. So that indicates a rather strong relationship, correct? Look at the graph from yesterday. We can see that it was linear, right? So it's okay to use correlation. We had 2 quantitative variables. Now there is one outlier, right? So that outlier was at 19,410. So I'm going to go in and delete that point and see what happens to the correlation. So if I delete 19,410, and I go back to stat calc and I go back to number 8, my R is now 0.836. Still strong, but not as strong, right? And that makes sense. That one outlier kind of pulled the eye down and made it more linear. Still linear when you take it out, but you had a more distinct line with that outlier. So it's good to look at it with and without the outlier. Okay, so in this case, I might say that with the outlier, the correlation coefficient is 0.96, and without, it's 0.84. Both of them indicate a rather strong relationship. There is no like perfect cutoff. Like I can't say it's very strong if it's 0.7 and above. Like that does not exist. That's going to be a judgment call. So it's going to be you looking at the graph, looking at the scatter plot, and looking at the correlation coefficient to make that judgment call. All right. I can't say that like 0.5 is moderately strong. Like there's no like cutoffs when you're looking from -1 to 1. It's kind of your opinion on how strong it is based on R and based on the scatter plot. Clay, did you find it? Okay, we'll find it in a second. All right. Any questions about what I just did? We good? Okay. Then here's the assignment. A lot of it is just looking at some statements and talking about why the statements are wrong. 11 and 12, they give you a bunch of scatter plots and you're matching the correlations to them. The stronger they are, more linear, the closer they are to 1 or -1. If you have questions, let me know. Look up how to